So this is equation 2, and basically what we want here is to find the tension in them, the cables, cable AB, cable BC, cable CD. And from what we are given, cables are looking like this, with they are forming an angle of 15 degrees here, and there's an unknown angle here that we're supposed to also find. We're also given the weight of the traffic lights, and we are given in kgs. We're given in kgs, so to convert that into Newton, we now use multiply by g. So the weight of the first object we get it's 10 kilogram times 10.81, we get 98.1, which is this. Okay. Second object, the second traffic light is 15 kilogram multiplied by 9.81, you get 147 Newton, which is here. Now we'll proceed now to find tension in our cables. Okay, so it's very easy. We will apply a method of joints to obtain the tension forces in the cables. Here we have two joints of 2 points. It's upon you to determine the one that you are going to begin with, but ideally you cannot begin from a point whereby you're going to work with two unknowns. What do I mean by two unknowns? You have this angle that is unknown, and you have the tension force here which is unknown. So you cannot solve for anything here. Here we have only one unknown, this tension force here. The angle here is known, okay? So it is prudent for you if you start from this point. So let us see, follow along. Now this is joint B. Joint B is the points are connected in this manner. So you're going to assume that you cannot see past here, okay? You cannot see past there, so you are dealing with here. Tension forces always point away from the joint. Okay, if this is the joint, the tension forces normally they face away. So this point gives us a diagram that looks like this. This is a vector diagram, a representation of the problem above here. So basically this is just what you can see here, and we proceed by finding the x and y, component of this one, because we are not going to find the x and y components of these ones because they are lying along the axis. This is lying along the y-axis, this is lying along the x-axis, and this one is lying in the xy plane. Okay, it has a y component and an x component. So this is going to be given by AB cos of this angle, which is here, AB cos of that, and the vertical component is given by AB sine of this angle. Okay, sine of that angle. The tension AB has both vertical and horizontal components because it's lying in the xy plane. Okay, and given here or not here, when a force is decomposed into its x and y components, it becomes fully represented by them. So we are not going to mention again about this force. It is now being represented by this because this one can be added to this one to give us a resultant force along the y-axis. We can add this one to give us a resultant force along the x-axis, because this is the next direction, this is the next direction, y direction. Okay, now we're saying since the system is in equilibrium, it means that the member forces balance each other. When they are balancing each other, it means when say the system is in equilibrium, it means we cannot see any motion. So the system is not moving; it is fixed. So the forces are balancing out; they are cancelling one another. So they are opposite and they're equal. So there's no motion. Okay. We apply the equilibrium equation by saying the sum of y is equals to 0 and sum of fx is equals to 0. So let us find the forces in the y direction. We have this one and this one. So because this one is going facing down and in a Cartesian plane, whereby if this is the origin, we have this is the negative side of the y, this is the positive side of the Cartesian plane. So that is where we have a negative here. It's a summation, but we have a negative here because it is a plus minus, you get minus. Okay. So when you move this one to the other side, you're going to have AB sine 15 is equal to 98.1. So you can solve for force AB. This is a force. Okay, this is a force. So force AB is given by, when you solve for AB, you get 379 kilonewton. So the tension force AB in cable AB is 379. So you have solved that using just this equation. Okay. Now to solve for BC will be given by summation of fx, because we have an equation here that tells us that sum of the forces in the x direction is equal to 0. Okay, so we are going to have sum of fx is equals to bc. The unknown, this is the only unknown that we are solving for. This was only the unknown that we are solving for in the y direction, so we are not going to look for it again. We have it, we have the value. Okay, so the summation of f of x is equals to bc. Bc in the x direction, it is positive plus negative of this, because it is facing the negative side of the x direction, and the sum is equals to 0 because they are in equilibrium, as you have said here. So we are going to have we have AB in our equation. Because we already know the value, we are going to substitute directly here. So we are having BC is equals to so if we take this one and move it to the other side of the equation, we are going to remain with BC. Okay, so BC equals to AB equals 15. But what is AB? AB is 379. So 379 equals 15 will give us the value BC. Okay. Yeah, and you are done with finding the forces in cable AB and the forces in cable BC. Okay, let us proceed. Now, before we proceed to point C, we have got this. Okay, this is a tension force AB, this is tension force AB, and this is the weight of traffic light, the first traffic light. Okay, and this is the given angle of 15 degrees. Okay, we shall see how tension BC will be used at point C or joint C. Okay, how will it be used at joint C? This is what we have. We said we cannot see from here. When you're at joint B, you cannot see beyond that. So now we are at this point, we cannot see this other point. Okay, we want to represent only this part. So that is what we have. So cable BC is also visible. It's also in this joint. Okay, so we're having the tension force facing like in that direction, away from the point. CD is facing away from the point, and this one is also facing away from the point, and this angle is unknown. I've given a note here saying that tension forces appear like this between 2 points. So if this is point B and this is point C, the tension forces are pointing away from the points. So it's like they are facing towards each other, but they are in equilibrium. So we're saying they are equal pointing away from the point. So if they are equal, it means that the value of BC will be carried forward. It will be used also in here. So we have 366 here as BC, and the weight of the traffic light, the second traffic light, we have an unknown angle here, and this one is lying in the XY plane, so it has the Y component and X component. So we have a sine of it and the cos of it represented as you can see. Okay. Proceeding to solving, we are saying that it is in equilibrium, so the summation of the forces in the x direction is equals to 0. Okay. So we have this force in the x direction, which is force in the negative direction. We are adding to the force that is facing, which is the x component of this force we have in that one. So by this you can solve for CD. So CD will be given by 366 over cos theta. Remember, we do not know the value of this angle, and we are going to determine that, we shall see. Now we are saying this is equation 2. The summation of Fy is equals to 0. Okay, y. So this one is facing the negative direction. Okay, this force, and we're adding it to the one that is facing to the positive direction. So and the sum is equals to 0. So we can say CD is given by CD sin theta is equal to 147. So that is given as equation 2. Now coming here, we're saying we substitute equation 1, this equation, into equation 2. Okay, here. So we're going to have this value CD. So we have CD here, and we also have CD here. So this value of CD will be substituted here. So we'll have 366 cos theta times sin theta is equals to 147. So we can solve from here. But we know that sin theta over cos theta equals tan theta. So this one and this one are going to give us a tan theta. So, and this one, when we divide both sides, 366 here and divide here by 366, we're going to get 1, and 147.15 over 366 is equals now to this value here. So that is where we're having this value. 147.15 over 366 is equals to tan theta. So we can get theta from here, isn't it? So theta is given by tan inverse of this value, which is equals to 21.9. And from there, now because we have the value of theta, we come back here and you find the force CD. Okay, the force CD, this force. Okay, so we substitute theta in equation 1, we have this, because equation 1 is right here. Okay, CD is equal to this is of cos theta here. So we have that. So we have already solved for all the member forces. We have the value of the angle, and we have AB, BC, and CD. Alright, and here we expected that theta to be greater than 15 degrees. As you can see from the equation, this angle here is bigger, because we're expecting that the post that is here is taller than the post that is on the, we have something that looks like this, like that. So this post that is supporting this side here is shorter. Okay, so they are not equal, so that is why this angle is bigger. Okay, thank you for watching.